Okay, here we go. AB number 3, worksheet 12.8. This is a multiple choice assignment. A little smaller than the last couple. I guess that's nice. We're going to cover inverse functions, derivatives, and optimization. Why don't you guys try the first 4 problems and pause the video and try the first 4 problems in the front. And then after you've tried them, unpause it and we'll talk about them. Okay, so suppose the derivative of f is, so this is a graph of the derivative. Which of the following could be a graph of f? So what you need to think about is like, well, this is positive everywhere. The derivative is always positive, so the graph has to be going up the whole time. This one's going down, this one's going down, this one's going down, this one's going up the whole time, this one's going up the whole time. So it's between D and E. Now, you'll notice that the slope is going towards 0 as we get further away. So that means the graph should be flattening out and not getting steeper. Its steepest point is right here in the middle. So that matches the steepest point here, and then it flattens out on both sides. Okay, number 2, the figure above shows the graph of f prime, the derivative of the graph of the function, open interval, -7, if f prime has 4 zeros. So f prime has 4 zeros. That's this, 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 and this. It's not the horizontal asymptotes. This is the graph of f prime. How many relative maxima does f have? Now, relative maxes. So this is negative, decreasing, positive, increasing, positive, increasing, negative, decreasing, positive, increasing. These are your critical points that might be relative maxes or mins. And so we use the first derivative test. We say, well, it's going up and down. This is a relative min. It's going up and then up. That's like a plateau. It's going up then down. This is a relative max. It's going down then up. This is a relative min. So this is your only relative max, and there's one of them. There you go. So these are quick problems. No real calculations, but being able to work off the graph of the derivative. Here's the graph of the derivative. Could you sketch the original graph? Not that you would have to do that directly, but problem 1 was like this. They give you the graph derivative, and you had to pick the correct original graph. Now, I would go through here and say, well, this is the graph of the derivative. So it's positive, increasing, positive, increasing. This is critical point, f prime is 0. Here's another f prime is 0. This is f double prime is negative, so it's concave down. F double prime is positive, so it's concave up. F double prime is positive, so it's concave up. Now I split it up because f double prime is actually not defined at 3 because there's a corner. F double prime is negative, concave down. So we do get an inflection point here and here. So that's a lot of good information. So when I sketch these graphs, I usually just kind of look at concavity. Is it concave up or down? And is it increasing or decreasing? So we'll start at like some C value plus C, unless they give us an initial condition. And then I'll break this up into pieces. And to help me, I think I'll draw these in. Okay, so this whole first piece, I'll just do it all at once. It has a slope of 2, by the way. So, that'd be like that to start with, right? Slope is 2. And it's going to end at a slope of 0. And it's going up, but it's concave down. So this first chunk is going to look kind of like this. And it should end with the 0 slope. Start with the 2 slope. This is f prime graph. F prime is 0 right there. The next chunk is going to be going up and concave up and end at a slope of 1. So maybe something like that. Slope of 1, not a slope of 0, slope of 1, and then it's going up more, and then approaches like a slope of 2, goes up even more, and it's concave up still. So maybe like that. And then it's still going up, but it is concave down to a slope of 1. And then it's still going up, but it's concave down to a slope of 0. So something like that. Okay, you won't have to do this specifically, draw a great graph by hand. But let's see. Number 4, use a graph of f prime, determine all these values. So, and then you could draw a sketch of it. So this is positive increasing. So this is graph of f prime. So this is what I usually do. Positive increasing, negative decreasing, positive increasing, concave down, right? Slope of the slope, concave up, concave up. You got to split it up because the concavity is actually 0 there. And then concave down here. So we have inflection point at 2 and 5. This is a critical point. This is a critical point. So this is going up and down. This is a relative max. Going down and up, this is a relative min. So tons of good information from the graph of the derivative. At what point do you have an inflection point? At x equals 2 and x equals 5. Where do you have a relative min? At x equals 3. Where's f increasing? 0 to 1. We typically include the endpoints for increasing, decreasing, and also 3 to 6, all one big chunk. Where is it decreasing and concave down at the same time? So here's decreasing, it's concave down here. So it's 1 to 2. Would we include the endpoint for 1 for decreasing? Yes, because it's the edge. Would we include it for concave down? Yes, because it's the middle of a concave down interval. Would we include 2 for decreasing? For sure. Would we include 2 for concave down? No, we don't include the endpoints for concavity. Sketch graph. This time you've been given an initial condition. And so we're kind of doing the same thing that we just did. And so we say, well, the first chunk is going up and it's concave down. Next chunk is going down and it is concave down. Next chunk is going down and it's concave up. Next chunk is going up and it's concave up. Next chunk is going up and it's still concave up. So maybe we should do something like that. Next chunk is going up, but it's concave down. So something like that. Okay. Let's talk about inverse functions. So we're going to do a little notes here. At the top, we're going to squeeze some notes in up here talking about inverse functions. You're for sure going to get some questions about inverse functions. So let's talk about some of the basics. Maybe draw a picture. This is just my function. So some of the things that we know about inverse functions is that the inverse is reflected across y equals x. Visually, that's what happens. And the reason that's happening is that your x and y coordinates are getting flipped and switching spots. And so visually, what's going to happen is that it's going to look like it gets reflected across y equals x. So AB on the original function becomes BA on the next function. Everything, x and y's get switched. Inverse functions, by the way, undo each other. So the other big thing now this is all stuff you guys should have known before calculus, but here's a new thing in calculus. The slope of the point here is going to correspond to a slope over here, and they're not going to be perpendicular, they're not going to be parallel, but the derivative of one either way is going to be the reciprocal of the other one, which totally makes sense, because if x's and y's are switching, then change in y over change in x is going to become change in x over change in y for the other one. It's going to be the same values but flipped. So those are the things that we want to use. And using this thing will allow you to not have to find inverse functions potentially. So let's try these first two together, and then you guys could try number 7 on your own, or either way. Or you can try them on your own first if you want. You could pause the video, try it on your own. If f is a function that is everywhere increasing in concave upwards. Now, if they hadn't given me a picture, I would have drawn a sketch kind of like this. Going up everywhere, concave up everywhere. Which statement is true about the inverse? Well, let's sketch it. That might make it a lot easier. So it's going to be going up everywhere, but concave down. It is a function. Okay. It is increasing in concave down. It is increasing in concave down. So I think that's your answer. It is decreasing. Nope. And concave up. Nope. It is decreasing. Nope. Concave down. Yes. So it's got to be C. But the sketch made that a lot easier. Okay. Number 6, the equation of a tangent line to the inverse. Well, we need a slope and a point. So x equals tangent line to the inverse at x equals 12. This is on the inverse function. Okay, so what we need to realize, I don't want to actually find the inverse function. I mean, we could do that. I guess I'll show that as a second way of doing it. And we could do it on this problem. But let's see. X is positive. This is the original function. Okay. Now, if x equals 12 on the inverse, then that means y equals 12 on the original function. And so what we're going to do is we're going to use that. We're going to set the y value equal to 12 and solve for x plus or minus. So x equals plus or minus 3 on f of x. Now, they told us x has to be positive, so we're going to go with the positive one. Okay. But if x equals 3 on the original, so y equals 12 on the original, x equals 3 on the original. So our point on the original is 3 comma 12. But if x equals 3 on the original, that's the y value on the inverse. So our coordinates on the inverse are 12 comma 3. Okay, so I'm trying to keep track of that. This is on f of x. This is on f inverse. Now, what I'd like to do is use this little thing right here and say, well, let's just find the slope of f, because that's super easy. It's just easy, and you don't have to do any other extra work. And then we got to make sure we don't plug 12 into it. We plug 3 into it, because that's the x value on that. And so this is the graph. This is the slope of the regular function, which means the slope of the inverse at 12 is the reciprocal of that. So that's the slope we want. And then we're going to write an equation of our tangent line, y minus, now use the points on the original function, or not on the inverse function, y minus 3 equals 1/6 x minus 12. Right? The other way of doing it, which is generally going to be a lot more work and just impossible sometimes. So the other way is to actually find the inverse function. I call this the old school way, because you guys learned how to find inverse functions back in like algebra. And so what you do is you take your function and you swap the x's and y's, and then you solve for the new y. And then you take square root of both sides, plus or minus. Now we're going to go with the plus, because if x is greater than 0 on the original, then that means that y is greater than 0 on the inverse function. So we're just taking the positive. So this is your inverse function, something we totally avoided doing. And then we can go and take the derivative of this. Now this is a messier derivative. So y prime equals 1/2 x minus 3 to the negative 1/2. And then you can plug 12 into this. you can also, what you're also going to do is you're going to use this to find the y value on the inverse. And then you're going to use this to find the slope, and then you're going to write your. It's just messier. And this is a really simple one for finding the inverse. Finding the inverse can be a lot more complicated and sometimes just impossible. So you're just going to have to use this new fact that the slopes are reciprocals. Go ahead and pause the video and try number 7. I would say try the new school way. You could try both ways to compare, but go ahead, pause the video and try it, and then we'll go over it. So we want the tangent line of the inverse at x equals 12 on the inverse. Now here's the original function. So the new way would be like, you know what? I just want to find the slope of this and flip it upside down. But you got to be careful because we got to say, okay, well, if x equals 12 on the inverse, and I'm usually just extra careful about this because it could easily get confusing, then y equals 12 on the original. So what I'm going to do is I'm going to plug that into the original for the y value and then solve for x. X minus 4, x plus 3, x equals 4, x equals negative 3. Now, this is on the original function, so we're going to take the positive one. And so if x equals 4 on the original function, so the point on the original function now is 4 comma 12, right? Which means 12 comma 4 is the point on the inverse that corresponds to it. So that's good to figure out. So what we're going to do is we're going to take the derivative of the original function, because it's super easy and we already have the function. We're going to plug 4 into it, not 12, 4 into it. And that's our slope. So now we can write the equation of the tangent line to the inverse, use the point on the inverse, y minus 4 equals 7 times x minus 12. Done. So, oh, shoot. Nope, just kidding. 1/7. So we still got to flip that slope. Still got to flip it. So that's I think the easy way, because the other way is to take the function and try and find the inverse. Now this one I made just a little bit more challenging than last, but still doable and still not that bad. To solve for y, you're going to have to complete the square, which I feel like people always hated doing back in the day, back in algebra 1, 2. It's always half the middle term squared. You're trying to get a perfect square, so this is 1/4. So we're adding something new here. You got to add it to the other side. And the reason you do that is because now if you factor this, it's going to give you y minus 1/2 squared. Y minus 1/2 times y minus 1/2. So now you have a complete square, and you can use that to solve for y. Square to both sides, plus or minus. Y equals plus or minus the square root of x plus 1/4 plus 1/2 to get the y by itself. Now we're going to go with the positive version, because if x is greater than 0 on the original function, then y is greater than 0 on the inverse. A domain issue in the original becomes a range issue on the inverse. So we found the function. So now we can find the y value that is on the inverse function. That's something we have to do if we're going to do it like this. And that's going to be what 49 over 4 plus 1/2 is going to be 7 halves, plus 1/2 is going to be 8 halves, is going to be 4. So there's your y value. And now you got to find the derivative of this ugly function, which is going to be 1/2 x plus 1/4 to the negative 1/2. And then you got to plug 12 into that. And that's going to be the square root of 12 plus 1/4. So that's going to be 1 over 2, 49 over 4 equals 7 halves equals 1/7. And now you can write the equation of your tangent line. Y minus 4 equals 1/7 x minus 12. Now, that was a lot more work, a lot messier work, and that's an example of one that's actually not bad. So we really want to use this approach, and you're going to be forced to a lot of times. Okay, let's talk about optimization. The major steps for optimization, we'll try and squeeze them in here, is we're trying to find an equation for the quantity to be optimized. So there's something we're trying to find the max or min of. So we need to get an equation for it, generally sometimes involving multiple variables. Then the second step is to get that equation in one variable. So there's usually some other restriction that will give you a relationship between the two variables, so you can rewrite as one variable. 3, we're going to take the derivative of our equation in one variable and set it equal to 0 or undefined so that we can find critical points. Right? Number 4, we're going to finish EVT. Endpoints, critical points, table, write your answer. So those are the major steps. Essentially, optimization problems are EVT problems applied to kind of real world problems, but a lot of times the biggest challenge of optimization is the lack of an equation to start with. And that doesn't really involve calculus. That usually involves geometry and just algebra steps to get there. So let's try a couple. We'll do 8 together. Rectangular field is bounded by the fence on 3 sides and river on the 4th side. Find the dimensions of the field for a maximal area enclosed by 1,000 feet of fence. So they've given you a perimeter amount of fence that you have to work with, which is going to be, one of your restrictions that's going to help you get your equation in one variable eventually. Now, this is rectangular, so those are equal. These are equal. I'm going to create a variable for those and another one for there. And we're trying to optimize the area. So the first step is that we get an equation for area, the thing we're trying to find the maximum of. The second step is that we don't want x and y's. We want all x's or all y's. So that's where the perimeter, which equals 1,000. But how do you write the perimeter here? The perimeter of fencing is 2 x's and 1 y. We're not going to build a fence on the river. So now we could solve for y in terms of x or x in terms of y. Either one. And plug it in up here so that we get a new equation in terms of one variable. Now, I kind of like this formula for certain steps of my work, but I also like this formula, this one for other ones. So the factored version is helpful sometimes, and the multiplied version is helpful sometimes. So far, no calculus. But that's where these problems are hard. Now, the calculus is, well, let's find the derivative of this and set it equal to 0 undefined so that we can find our critical points. So that's going to be 1,000 equals 4x divided by 4. X equals 250 is your lone critical point. Your endpoints. Now, this is another challenge of these. A lot of times the endpoints, usually on absolute maximum problems that aren't optimization, the endpoints are usually just given to you or just stated. But these ones, you got to think about it. You got to use some logic. Now, if we had changed everything in terms of y, then endpoints would be in terms of y, would be different. We'll get the same answers in the end. What's the smallest x could be realistically? 0, right? You could just have no fence there. What's the biggest x could be? Well, the biggest x could be is usually when y is the smallest because they work together to give you the perimeter. So the smallest y could be, I think, is easier to determine in your head. It's 0. So then you set it equal here, and then you get x is 500. So when y is 0, the less you use for y, the more you have for x. So those are your endpoints. So we're going to make a table 0, 250, 500. We're going to plug them into our area formula. Now, this is where I like the factored version because I feel like it makes it easier to do the work in my head. And it also shows me this right here is the y. So it'll kind of show me what the y values in my work. So this is going to be 0 times 1,000 is 0. Then we're going to get 250 times 1,000 minus 500 is 500. And that's going to be 125 with 3 zeros after it. And then 500, that's going to be 500 times 0 is 0. Now, these endpoints a lot of times are kind of like stupid situations where you're building the fence right up next to each other. But here's your max. Here's the x value. Here's the y value at the max. So they might want to know both of those things. Now, they didn't. I created x and y, so I should probably describe my answer not in terms of x and y. If I do, make sure you have it on your picture. But might want to describe it more in terms of like the problem. So I might say the maximum enclosed area is 125,000. Now we want to put units here, I think, right? We have units, feet squared when the side's perpendicular to the river, instead of saying x, are 250 feet, and the side parallel to the river is 500 feet by extreme value theorem, checking endpoints and critical points. So that's a really good thorough answer. Tells you what the max is, where it is, justifies it all. So that's optimization. So I want you guys to try one. Why don't you guys try number 9? Pause the video. Try number 9. Make sure you know how to do these. They're going to be on your next practice test. You saw them on your previous practice test. If all you do is copy my work here, you are not ready. So try it. Okay, rectangular area of, now here they're giving us the area. Instead of us trying to find the area, they're giving us the area. They're probably going to ask us to try and find the side. 2 opposite sides of fencing costing $1 per foot, and the other sides are costing $2 per foot. Now, it doesn't really matter like which ones we put these on. It'll work out. Now, if they hadn't given you a picture, I would have drawn a picture. But you know that 2 opposite sides are equal. 2 opposite sides are equal. It's a rectangle. Whatever. We'll make this $1 a foot and this $1 a foot, and we'll make the other ones $2 a foot. It could come out that the $1 per foot ones are shorter than these. This is just a way to organize your information. I should create some variables. We could call these x and y and y. Now you want to create the least amount of variables possible. You don't want to just say x, y, z, w, like what are we trying to find? The dimensions of the rectangle with the least cost. So we're trying to minimize cost here. So we need to come up with a cost function. Now, cost equals quantity times price. So that's going to be 1x plus 1x plus 2y plus 2y. So cost equals 2x plus 4y. All right, cool. We got an equation. Now we got to get in terms of one variable. So there's some other restriction. It says that the area has to be, there's another relationship for x and y. The area x times y has to be 3,200. We have to have that much area. which means we could get this in terms of one variable or the other. We could say, well, y equals 3,200 over x, or the other way around. So cost equals 2x plus 4 times 3,200 y. So that's our cost function in terms of one variable, 64, 128 over 0 if we want. Right, 2 times 64, 128 over x. So there's a cost function, one variable. So now we need to start doing the calculus. We're going to find the derivative, c prime, which equals 2 plus. Now, instead of doing quotient rule here, I'm going to think of this as x to the negative 1. So that's going to be minus 128, 0, 0, x to the negative 2. And that's easier than quotient rule. You can do quotient rule if you want. Might rewrite this as 2 minus 12800 over x squared. So there's, now we're going to set it equal to 0 and define. Now, I don't know if you guys remember back from Unit 1 when reviewing all the algebra stuff we need. Be careful about cross multiplying. You're going to lose the undefined answer. So right here, x cannot be 0. That's a potential critical point. But to find the other one, so usually what I do is I keep it all on one side, equals 0. I give the least common denominator, 2x squared minus 128, over x squared equals 0 and define. And so x equals 0. And here, I'm going to set the top equal to 0 and then solve it. Plus or minus 80. Now, the endpoints are going to be, kind of running out of room here, the endpoints, let's see, for x, the way I've labeled it, the smallest x could be, well, it can't technically be 0. So it can go all the way to 0, but not include 0. And the biggest x could be, well, what's the smallest y could be? Well, the smallest y could be is it could approach 0. Now, the reason they can't be 0 is because if x equals 0, you don't get an area anymore. And it says you have to have an area of 3,200. So as x gets really small, y gets really big to still make up for the 3,200 square feet. When y gets really small, x gets really big, goes to infinity. So what this means is we don't have a closed interval. We have an open interval. We can't technically do extreme value theorem. Okay, now we could use the ideas of it to kind of help us figure it out. And say, well, the limit as x goes to 0, and then plug in 80. Now, negative 80 doesn't get considered because it's outside our endpoints. You can't make a negative fence. And the limit as x goes to infinity. Now, as x goes to 0 here, that goes to 0, that blows up, and your cost goes to infinity. As this goes to infinity, that goes to 0, your cost goes to infinity. And when you plug 80 in, you get 160 plus 128 over 80. And we could say, well, that's 640, 320, 160. So the whole thing is going to be 320. The cost is 320. Now, what's the smallest cost? Infinity, or 320? Well, this is definitely the smallest. So that's your minimum. It's $320 when the $1 per foot fence costs, we have 80 feet of the $1 per foot fence. And then what's the Y? 40 feet of the $2 per foot fencing. So instead of using X and Y, maybe refer to the size. So we could say the least cost is $320 when we use 80 feet of the $1 per foot fence and 40 feet of the $2 per foot fence. So that's the answer. Then you say by extreme value theorem, checking endpoints and critical points. Well, actually, no, we can't really say extreme value theorem here. So that wouldn't be a good. If it, for response, you now have your work cut out for you. Now, what we could have done is when we realized we couldn't do extreme value theorem, we could have also tried to use first derivative test and did a line check for C prime, put the critical points on here. And by the way, that critical point x0 bounces off the graph, test a value, I don't know, x equals 1 will be positive, positive, negative, negative. So it's going down, up, down. But then we use our endpoint. So we say, well, it's between 0 and infinity. And so this is a relative max, but because it's the only peak or valley in the whole, only relative extrema, it is the absolute extrema because the graph just goes down forever. So then you would justify, you would state that this is relative max and justify it by the first derivative test for relative extrema. Then you would tell me why that relative max is an absolute max. So in free response, you really want to avoid that because it's a lot of work to justify that way. Extreme value theorem is the best way to go as long as you can use it. Okay. I'm going to let you guys do the next problem as homework. So you can check your work later on mine. We have some other problems here, just some, we could try a couple of these odds and ends. These are just like problems that we've done before now. This right here, you should look at and say, hey, that looks like a derivative. And you say, well, what's the function that we're taking the derivative of? It shows up twice. It shows up like here and here, right? This is because it's like f of x plus h minus f of x. And so this function just has multiple terms. I bet it's 2x to the fifth minus 5x cubed. And here you'd be like, but it's a plus. Yeah, because if we put parentheses around it, it would have been a minus, and then you distribute the negative, and it makes it a plus. So that's your function. The derivative of that is 10x to the fourth minus 15x squared. And then that's it. 10x to the fourth plus minus 15x squared. So I'm gonna let you guys try these problems on your own. They're reviewed from stuff that's been on other multiple choice packets. We have some more problems on the back with some tables. Probably got to use some estimation techniques, or this is like a function table. So I would find the derivative first in generic terms with f and g's, and then plug in the right values. There's a product rule here, right? Product rule. So you guys are going to finish the rest of this homework on your own. The answers should be up to check. At least just check if you got the right answer, and if you got the wrong one, see if you can fix it. Figure out why you got it wrong, and then I'll put the work up eventually later so that you can really figure out your work. That's it.